Hi. My name is Merlin. So I'm just gonna talk about what I learned today. Um, actually, the thing is that I should have taken this video yesterday, but I was really tired. But I don't like, mm, like I slept like 13 hours and I haven't recovered yet because like last week and this month and the past month I worked so hard on my project on my service thing, so I'm just gonna push myself that because I didn't take this video, so I'm just gonna take the video that has the better quality than yesterday and past month. So the today the main topic is the B-tree. So what is B-tree? Why do we need B-tree algorithm? Because I work in data structure. I know as a B-tree as a data structure that implements the binary tree. But the thing is that what I have to say is, you my recommendation is the B-tree is kind of complex data structure, and I think also it's kind of also algorithm, and also this B-tree isn't just came out because of the limitation of the binary tree. Um, the computer science history isn't just it just isn't just made of that the past version of some kind of specific technology is just just slow or not. The computer it has background of it. It has because I mean like we are software engineer and there are some every way we face problem and we somehow solve it, and if it's like repeated and tedious and we're just gonna abstract we're just gonna try to make an abstract layer to make a new concept. And I think the also data structure algorithm or other thing is same as this. So why do we need B-tree? So to understand this, you have to understand the kind of database thing. Um, let's say you have a some kind you want to store your employee. Let's say employee. Of course, if you get a job, you might have the unique ID or unique your number of your title. So there's gonna be ID that has to be unique. And also, you are female or male. You have a gender. And also, what else? You have a name. Let's say male, ID 0. Name. Let's say my name is Merlin. So let's say Merlin. So those kind of thing. Those kind of unit of data is called record. And in this record, the key is the ID. The meaning of the key is the unique, specific identifier in record or some kind of unit of data. And that's very fine. But what and there's a like you are I'm like you are being part of like one of the largest company, example like Amazon, what else, whatever. So there are example 10,000 of employees. And there's a bunch of record of the 10,000 employees. And let's say you wanna find some kind of employees that has ID number 90. Let's say 1005. So let's say ID is 1005, and you have to traverse all of the records, and you have to go inside this of the record box, and you have to check it out the ID, and but it's kind of tedious. I mean like you have to really try to go inside the record and you have to look at the key. But why don't we just collect only the ID, the key part of the record, and make a file of it? So that's called the index file. And so index file is just the set of your record kits. But there's a problem we also face. And let's say and there are like bunch of IDs because we just say the key, record key is the ID. Let's say the um, ID is just in the box. I'm just in the box, like a worm. Like let's say like this. So let's say like this. I'm really bad at drawing, and there are like there's a it's kind of linear, and there's an ID and ID 10,000 over 10,000, and but that's kind of nice. But what if we say we only get the value of ID 10,000? We only search about the ID 10,000. That means that we have to really traverse like the 0 to the 10,000, which is kind of slow, which is really slow. If it's 10,000, it could be, I don't know. I'm not big an software engineer, but if it's like 10,000, like million, that's gonna be issue of it. So due to this kind of the limitation or problems, we trying to say those kind of things, those kind of data structure, array isn't really efficient. Why don't we just make it tree? Let's we call as the binary tree. And so the binary tree is you put the small value on the left and bigger value on the right. Let's say 5, 4, 6, 3, 6, 5, 8, like this. So hold on, 7, 9. But there's a 10. Okay, like this. So this kind of like example of the binary tree. Yes, when you try to insert some kind of the value, example you want to insert the 1, you just have to go to you just have to compare the node of it. Example, the 1 is smaller than 6, you go left, and 1 is smaller than 4, you go left. 1 is smaller than 3, and you also go left, and you have to insert it like here. And that's very nice, and that's really nice. And those kind of things make it more faster. Since this kind of way is kind of the input, the example, if you're the input, the time goes by the same time when input grows. Yeah, I'm sorry, my pronunciation is bad. Let's go ON, the time complexity is ON. I mean, like, don't be really think about complex. It's just you have to traverse 0 to 10,000, and N is 10,000, and you just have a linear data structure, and it's ON. I'm like, it's obvious. Binary tree is, but since let's say you wanna find the number 5, when you're trying to traverse to find the 5, we can just go to this root. I'm just gonna like mark that is have visited. So it is visited, and this part is visited, and this part is visited. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 of the elements, but we traversed only 3 nodes. So that's kind of really efficient than this part. So the time complexity, the binary tree is log n. But the thing is that's very nice. But what if you wanna find the 10? So let's say our target is 10. We mark this part, and we traverse this part, and we just traverse this part, and we just traverse this part, and you just traverse this part. So 1, 2, 3, 4. And but the thing is that I think you already noticed that when this tree of root, the depth of the tree grows, the more nodes has to be visited. So if your more nodes has to be visited, that's kind of very similar to the array data structure. So the worst case is O log n. ON is worst case same as the data structure or data structure. So our great software engineers, our great people in our computer science industry, and they think about the problem of the binary tree is that the node can have only one children. Why don't we make it put like multiple value in one node and make it the tree as stable? So this kind of binary tree is a B tree is just being made. So B tree is kind of really it's really kind of complex, but it's kind of interesting data structure. Let's say I'm just gonna draw it for you. Let's say your max your max keys that node can have is, let's say, 3. So let's say we insert 5, 4, 3, 1, 6, 1, 4, 3, 1, 5, 8, 7, 9, 10. Let's say we just insert this. I don't know if you can see or not, but let's say you have this kind of array to insert. The normal binary tree is you have to just compare it and you just have to go put on the left, but it's sort of saying it's just the B tree is extended version of the binary tree. So let's do it, and I don't know if you can see or not. So you have to insert 6, 4, 6, 3, 4. And your max key is 3, and it's already 4 of the capacity, right? So it's really ready to split into the node. Why do we need split into node? Because we just set the limitation of the max keys that node can handle. So let's say next part we insert the 1 value. Since when we're trying to insert the 1 value, this is full. So we have to make some key to go to the parent to make it 3. So to find the primary key, it's called a primary key to promote to the parent. So to look at the primary key, we can just go to the middle part of your node. So if you look at the formula of the B tree is, if you give the minimum degree, let's say 3, let's say 2, the max keys that node can handle is 2t minus 1. So which means that the value, the key length is always the odd. So of course we have 3, and the primary key index is 2t minus 1, which is 1. So 0, 1, 2, our primary key is 4. So we have to make the 4 into parent. And so this is gonna be like 3, 4, 6. And let's say we only insert 1. You have to know that if you're trying to insert it, you have to insert only on the left. You have to keep your mind, you have to insert only on the left. Let's say you only insert 1, so you just simply like the binary tree, you just have to compare the value and you just have to insert it. So since 1 is smaller than 4 and 1 is next to 3, you just have to insert it like this. This is 1, 3. And next day we just do same stuff. 5, we go with this part, 5, and 8, we go with this part. But since the 7, when trying to insert 7, this is already 4, right? We just have to select the primary key and like what we did, and we just have to assign it into parent. Since 6 is the primary key, 1, 3, we just have to merge it with the 6. And 6, yeah, we just have to merge it, and this is go to 5, and this go to 8. And you just have to put the 7 underneath here. Next thing, 9 and 10, and it go like this. 8, yeah, those kind of things. 10. So if you look at how this works, if you're trying to insert the 9, it's already so full. You have to make it to parent. So like this 9, put 9 here. I think put 6 here and like I'm gonna try to reverse it. 9, put like this. 4, 6, 1, 3, and put 5 here. Put 7 here. 7 here. Put 7 here. Put, yes, put 8 here. 6, 8. Put 4, 6. Wait, hold on. Say 6, 8, 7, 8. You're going to try to put 9. 8 goes here. 9 goes here. So 8 goes here. 8 goes here. Yes, 9 goes here. And 9 goes here. I think it's like this. Goes like 11. Yeah, we insert 10 here. Oh yeah, we don't have to remake it like this. 6, 8 here. You don't have to remake it like this. 6, 9. Yeah. So I'm sorry, because I'm really bad like those kind of making like here. 5, 6, 9. 5, 6, 9. 4, 6, 9. But whatever. I'm sorry, but I think I already demonstrated what it is. But so you just have to select the primary key to put it the parent. I think I need more study of this. So the problem is like I just did. So there's a primary key has to promote. If you're trying to merge it into parent, there's a primary key to promote. So those kind of like the propagation of the insertions making this confused, and this kind of insertion on the B tree. But I think the most important part, I think the most hard part is deletion. So let's say for 6, 4, let's say we have 4, 6, 8, 1 and 3, and 5. It was like 7, 8, 9. So let's say like this. This is our B tree, and I'm talking about deletion. So if you're trying to delete the one part, and you have to really validate if your node have a minimum key or not. So the minimum key in the formula is also t minus 1. Since our t is 2, minimum degree is 2, our minimum key that node can have is the 1. If we try to delete 1, it's still valid, but if you're trying to delete 3, there's gonna be more problem. Let's say if we're trying to delete 5. If you're trying to delete 5 in the B tree, you have to borrow from the siblings. You have to borrow from here or here. Let's say we just keep alive the 1, let's delete the 5. So we just have to pick the 1 to borrow. So let's say we're gonna go to the right. So we have to get the 6 and we put the bottom here and put the 7 as a parent. So the 6 goes down here, the 7 goes here. So if you're trying to delete 5, it's still stable. So this kind of deletion is come from. But let's say we just delete this kind of 1, 3. My drawing is really bad. 4, 7, 1, 3, 6, 8, 9. Let's say we already delete 3 and we delete 1. Since we have to borrow from the next siblings, but if you're trying to borrow siblings is gonna be also gonna be none, so it will just be like this. So our way is, so this is another way. Yes, we are already already done. So what we have to do is borrow from the parent. So this is the parent is the 4. We have to borrow. So let's say we just already delete 3. Our correct key to delete is 1. So what we have to do is merge 4 and 6. And that's gonna be 8, 9. And you have to just delete the 1 here. That's gonna be simple. But that's kind of very easy way. But if, let's say, if you only have 4 here, let's say you don't have those kind of thing. If you're trying to delete 1 here, since the 4, if you're trying to borrow from the 4, that's gonna be more issue. So another way is, if there's a parent, you check out is the parent has the minimum key or not. And next part is you should have to borrow from the parent also. So those kind of deletion is kind of hard. Insertion is kind of but easy, but if you look at the deletion, you have to think about like a lot of things to do. But our key thing is that the database, the B-tree is using in the database indexing algorithm. But you really have to give question of why. The database has to be alive, even though you turn off your computer. That's called non-volatile. It has to be stored in non-volatile memory, which is the disk, and to go to the disk to get the data from the disk is slow. So what that means slow? Let me just try to explain with you some kind of easier computer architecture. In the processor, processor, let's say CPU, you have a register. You have a general purpose of the register, and you have special purpose of the register. And normally you store those kind of general purpose of the register and special purpose of the register. So the register is just like storage in here. And let's say, and also, you have a bunch of instructions to do something. You have to tell CPU to do something. And since there's no concurrency in the low level without OS, if you're looking at assembly, there's no concurrency on there. See, assembly, the computer can run one instruction per time. So other instructions have to be stored in the memory. So the memory, to get some kind of resource from the memory, you have to ask for the fetch. And next time, when you're trying to get the instruction via fetch from the memory, we have to decode it and you have to execute it. Moreover, this kind of fetch cycle, those kind of instruction fetch cycle, is also being held by the bus. It's not really not being handled by bus. There's a hashtag bus on it. So what do you mean bus? The bus is just it's just like highway. If you're trying to at the first, if you have experience of the driving, the first highway is that you can surpass other cars, right? The second is, I think, the normal vehicle. The third is like a large vehicle, like truck thing. So this is really kind of simple, similar to the bus. There's our data bus, others bus, and also control signal bus. So the data bus, and it just be like some kind of like highway that you can you can send something, but only for the data. Since if you look at the fetch cycle, yes, when you're trying to ask for the fetch, so it's gonna retrieve the data. So that's gonna be data bus has to be done in here, and the address bus it has to be done here because you ask for some kind of specific value from this address. So address gonna be here. So address bus, but control signal is bus is the one who receives the state of memory X. Example, read, write, read and write, those kind of thing. So those kind of thing is actually aimed to get the main memory or the whatever memory from the memory here. But if it's like some kind of disk that is not part of the processor inside the CPU, it's not really directly like associated. So it's really far. So you really have to think about those kind of latencies, kind of it. So that's why we really have to think about the speed when trying to do the indexing, because I know operating system handle those kind of memory management, also disk memory management, but even though it's really kind of slow than the like getting some kind of data from the RAM. So that's why we made some kind of B3 stuff. So I think this is it. Have a nice day. See you next time. Bye bye.